Uh,
My screen is visible.
yes, sir. Let's start.
Yes, sir.
You can hide this here. Yeah. Yes, please.
So, hello all. Welcome to the IT and Gate classes. So, in this particular session, we are going to discuss fluid mechanics question, which is being asked in UPSC DGCA ASO exam, right? So, all of you, please confirm whether I'm audible or not in the chat section. Okay, guys. So, in this particular, session, we are going to discuss fluid mechanics question, right? So, this is nothing but set B, fluid mechanics. So, this is the first question we are discussing. Right. So in this particular session, I'm marking it as question number one. Right. In examination, it was given as a question number 45. This particular question, right? Now, when you read this question, what they have given, the slope of the velocity profile at the wall is of a particular importance, right? Because it governs the wall's area stress. Let du by dy at y is equal to 0 be defined as velocity gradient at the wall. Mu is nothing but absolute viscosity coefficient. W indicates the wall, and they are asking what is the wall's air stress. What is the air stress at the wall, right? So this is one of the easy question as far as the fluid mechanics is concerned. So first of all, let me give you small idea about this question. So generally, if I talk about flat plate problem, suppose plate is fixed, the bottom plate is fixed one, and we have the top plate. For example, it is moving with some velocity with some constant velocity, let's say. And we have some velocity profile which is not known to us. The velocity profile can be anything. For example, a general case I'm considering a velocity profile as a cubical or parabolic velocity profile. So what I'm doing, I'm marking here it is this one. Now, what is the slope of this velocity profile? So this I'm marking with the different color here. So this particular value, this theta, right? So what is this theta I'm writing here? Du by dy. In generally fluid mechanics, we say slope rate, right? So we say theta dot du by dy, right? So that is the slope of this particular velocity profile, right? Du by dy. Now it is having certain importance. Again, in the question they have given du by dy, so I'm writing it as du by dy. Let's say it is given as u is equal to constant. U is equal to constant. Now we also know that according to Newton's law of viscosity, now, what is the Newton's law of viscosity? Everybody know that the shear stress is directly proportional to du by dy. If I talk about the Newtonian fluids, so this particular law will be applicable. Now, in this law, if I remove the proportionality constant, I will be getting one proportionality constant. That is nothing but tau is equal to mu into du by dy. Again, I am writing dv by dy because in the problem they have given dv, not du. So let me write in that way. So that is particular law which is known as Newton's law of viscosity. Newton's law of viscosity. Now, when you think about this particular option, which option is missing? Now, here they are asking what is the wall shear stress? That means this is the wall. For example, this is the wall I'm marking, and we know that y is the distance from the wall all the time. So what I'm calculating y exactly at a zero. When the y is equal to zero, then this is nothing but what? Tau wall, right? That means what? Mu into dv by dy exactly at y is equal to 0. So which option is correct? Any one of you? . by looking at the options, which option is correct? A option is correct, right? Because B is given as mu into dy by dv, that is incorrect. Again, minus, there is no minus here. This is also incorrect. And what about D? Again, it is not been multiplied with the proportionality constant. Because if you remove the proportionality constant, if you just try to convert this one into the, whenever you are equating the tau versus du by dy, definitely one proportionality constant will be coming. That is nothing but viscosity. And that viscosity we are calling what? Absolute viscosity coefficient. So that is regarding question number 45. Right? So A is correct. Now coming back to the question number 2. Note down first of all. Question number 2. A wooden block in the form of a rectangular prism which is floating with its axis vertical. The block is 40 centimeter long, 20 centimeter wide, and 50 centimeter deep. With the depth of immersion of 12 centimeter, what is the position of a meta center? And they are asking comment on the stability on the block. So first of all, what I'm doing, I'm just making the diagram for you to understand. So first of all, there is a cubical block. So this is what the cubical block they have given in the problem. And the depth of immersion, basically they have given as, from the free surface, the depth of immersion is given as 12 centimeter. This much of height of the liquid, height of the block is under what? Water. Now what is the value? 12 centimeter. Now here, what else they have given? They have given the height of this particular block. If you just go back and see this, the block is 40 centimeter long and 12 centimeter wide, 20 centimeter wide. And what is the total depth? It's a 15 centimeter. What is the length? The length is given as 40 centimeter. No doubt. So first of all, they are asking what is the distance between the meta center point from the center of gravity. That means they are asking GM. No doubt. GM. Now, what is the formula for GM? That is from the concept of buoyancy and stability. Everybody must know what is the formula for GM. That is nothing but I minimum by volume of the liquid which is being displaced by the block minus Bg. Hold on, I will discuss each and everything. First of all, note on this one. I minimum is nothing but a minimum moment of inertia. Minimum moment of inertia. Minimum moment of inertia of the plane cutted by the fluid surface, cutted by the free surface level of the liquid. Free surface level of the liquid. The minimum moment of inertia of the plane which is being cutted by, the free surface level of the liquid. This is the free surface, right? This particular surface we are calling free surface where the shear stress is 0. Now, what will be the next thing? What is the value of Bg? The distance between center of gravity and center of buoyancy. distance of center of gravity and center of buoyancy. Then what is the value of GM? Distance between metacentric point and center of gravity. If this particular GM value is more than 0, always remember, for a floating body, we require the metacentric point m value only for floating body, not for the completely submerged body. For a completely submerged body, G and B point will be sufficient to tell about the stability or instability of a particular system. But here, for a floating body, we need the G M point also. Along with the B and G, we need M also. M always should be above the point G. And if GM will be more than 0, that means what is the GM? The distance between M minus G. All of you understanding? Please confirm it. M must be above the G, right? That means we say it's a stable condition. If GM will be equal to 0, then we say it is a neutral condition. If GM will be less than 0, then we say it is unstable, condition. Now let us calculate what the value we are getting in our particular problem, right? In our particular problem, what is the value of GM? First of all, what is the minimum moment of inertia? Hold on. First of all, what is the minimum moment of inertia? So minimum moment of inertia, for calculation of a minimum moment of inertia, first of all, we need to cut the plane. First of all, we need to cut the plane, by the free surface level of the liquid. When you cut it, you will be getting something like this. When you try to cut it, you will be getting something like this one. This particular plane you are going to get. I'm marking here, I'm just highlighting with the dotted line. This particular plane you are going to get. When this free surface, when it cut it, definitely you are going to get this particular rectangle. I'm just drawing the rectangle once again. Now, if you see the rectangle, what is the width of the rectangle? 20 centimeter. Width of the rectangle is 20 centimeter. Now, what is the length of the rectangles? 40 centimeter. You can see very clearly the what is the width and what is the what we call depth. You call 40 centimeter, right? Now we can calculate the minimum moment. We can calculate the moment of inertia about two axes. I'm calling this axis, for example, if you just say this axis to be as xx and this axis to be yy. So what you do, you calculate ixx. If you calculate ixx, you are going to get 20 into 40 cube by 12 centimeter to the power 4. And if you calculate iyy, you are going to get 40 into 20 cube divided by 12 centimeter to the power 4. Out of this two, which is the minimum one? So minimum value will be what? Iyy. Because it is the minimum. Because it's a 20 cube, there is what? 40 cube. Now what is the next particular task? We need to calculate I minimum by the volume which is displaced by this particular volume, which is being volume of the liquid which is being displaced by the block. Now tell me how much of volume of the liquid which is being displaced by the block? This much of volume. This much of volume of the liquid is getting displaced by this particular block, because that much of depth of immersion is there. So that much of particularly volume of the liquid is getting what? Displaced. The red marking which we have done here. So what is the volume? I minimum, we know that it's a 40 into 20 cube divided by 12. Now what is the volume of the liquid which is being displaced? So it is nothing but I'm writing volume is what? 40 into what, guys? How to calculate the volume? 20, 12 into 40. 20, 12, 20, 12 into 40. That is the volume. If you try to calculate in centimeter, what is the value you are going to get? 40 into 20 whole cube divided by 12 divided by 40 divided by 12 divided by 20. So you are going to get 2.78 centimeter approximately. So that is the value of I minimum by volume displaced. Now tell me how to calculate BG, the distance between G and B. It's a very simple, guys. Let me mark it. What I'm doing, I'm just removing some red marking here. Center of buoyancy is nothing but it is a centroid of the liquid which is being displaced by the block. How much of volume is getting displaced? This much of volume. I'm marking with the blue color here. Now tell me what is the centroid of this blue marking? 12 by 2. So I'm marking this as a B. And what is the distance from the bottom surface? It's a 6 centimeter. Now tell me what is the centroid or center of gravity of this whole block from the bottom surface? What is the value of G? The value of G will be, it's a total value is 15, 15 divided by 2. So it is nothing but what, guys? 7.5 centimeter. Now tell me what is the distance between G and B? 15 by 2, that is a 7.5 minus 6. So what is the value? 7.5 minus 6, 1.5 centimeter. Obviously, you can get here GM value as I minimum by volume displaced minus BG. So what is the I minimum by volume displaced? 2.78 minus 1.5. Now, can you tell me the value here? 2.78 minus 1.5, you are going to get 1.28. You are going to get 1.28. Note down. 1.28 centimeter. We are getting more than 0 means what? It's a stable condition. It's a stable condition. Now, when you look at the options, what the option they have given? Comment the stability of the block and what is the position of a meta center. That means what is the value of M with respect to G. So it is 1.28. Approximately we got 1.28, but it is 1.278. Right. So we can round out to what? 1.28 centimeter. And the body is under what? Stable equilibrium conditions. A option must be correct. A should be correct. Is that clear? All of you understanding? Is this particular question is clear? Question number 46. So that we can move on. Done, guys? So this is the whole concept which we have discussed here, right? Now, question number 47, which is nothing but question number 3 for our today's session. Consider the following statement regarding this particular surface tensions, right? So first of all, note down the questions. Again, it is one of the pretty straightforward questions. Pretty straightforward question you can see here. They are asking about the surface tensions. Now, when you see the surface tension, definitely because of the surface tension, what will be there? The concave, whatever the surface will be there, that surface will no longer will be flat. There will be some concavity will be produced in the particular surface. Now, how to calculate those concavity? By balancing the forces, right? By balancing the forces. How to balance the force? How to balance the forces? Tell you guys. So first statement they are asking, the pressure inside the droplet or a soap bubble will be higher than the surrounding atmosphere, which is obviously correct. I will discuss why. The pressure inside will be higher, smaller will be the size of the droplet. The pressure inside the droplet of a soap bubble will be less than the surrounding atmosphere. Now, when you look at the options, they have given which of the following statements are correct? 2 and 3, 1 and 2, 1 and 3, 1, 2, 3. Right. So first of all, we will discuss how the droplet formations is taking place. How the droplet formations are taking place. So what I'm doing, I'm discussing here. Solution number 47. Let me discuss the very fundamental concept here. For example, one by one we will discuss here. Suppose we have a flat surface. if I have P1 here and P2 here, that means P1 is the inside pressure and P2 is the outside pressure. And for example, this is a surface. If surface is a flat surface, then definitely P1 is equal to P2. But for example, we have a surface like this. Why this surface is formed like this shape? For example, P1 is the inside pressure and P2 is the outside pressure. If P1 is more than P2, definitely this will be the shape, no doubt about it. Again, we also have a shape something like this also. If let's say P1 is the inside pressure, P2 is the outside pressure. If again P1 is more than P2, definitely we are going to have this type of surfaces. What I want to say, what is the reason of droplet formation? These are the reasons. Because of this, there is a formation of a droplet. A formation of a droplet. Surface will no longer will be flat whenever there is a difference of pressure, and that will cause because of what surface tension, my dear friend. Let's say we will discuss some droplet formation. Let me derive it so that you can understand what is a theoretical question. Droplet formations. We have a droplet of the liquid like this. What I'm doing, I'm just cutting by this plane. I'm just cutting by x plane, and I'm showing here only the left part of it. If you consider only the left part of it, then you are going to get the now you can imagine this is a half part of the droplet where, my dear friend, at the surface you're gonna have surface tension force like this. It will be acting only on the along the length of the surface or perimeter. Now, my dear friend, you know that inside the pressure is what? Total pressure is PT. Inside whatever the pressure is there, that is a PT. And outside of this bubble, everybody know that what is the pressure? Whatever the bubble is there, that is not there in the space or vacuum. It is there in the atmospheric conditions. Whatever the pressure is there, that is the atmospheric pressure. Now, my dear friend, tell me, if PT is more than PATM, obviously, while looking at this shape, you also know that everybody know that. Let's say PT is what? P1 and PATM is what? For example, P2. Just follow this particular diagram. Why this particular shape is forming when the P1 is more than P2? Definitely, total pressure inside this bubble or this droplet is more than PATM. This difference of pressure I'm calling delta P, for example. Because of this delta P multiply with the area, projected area, that will give me bursting force. What it will give me? It will give me bursting force. For example, that particular bursting force will try to balance it out by the what? Surface tension force. So if I do the force balancing, what I will be getting? Delta P multiply with the projected area. What is the projected area? Pi r square, because it's look like a circle when you project it, where r is the radius of this particular what we call droplet. That is equal to surface tension. Now surface tension will be acting along this perimeter. What is the perimeter? 2 pi r. So from here, what is the value of delta P? It's a 2 sigma by r. In terms of diameter, what we can write? In terms of diameter, we can write 4 sigma by, where d is nothing but the diameter of a droplet. So this is what the air bubble you are having. This is what the air bubble you are having. If you are having the soap bubble, definitely delta P will be what? 2 times of this value. If you are having a soap bubble, because in that case there will be two surface, so 2 times surface tension force will be coming. So in that soap bubble, the delta P will be 8 sigma by T. Now come back to the question, what they are asking. The question they are asking, the pressure inside the droplet or a soap bubble will be higher than the surrounding atmosphere. Obviously, this statement is correct. Obviously, this statement has to be correct, right? What about the second statement? The pressure inside will be the higher. Let's suppose for droplet, we are having 4 sigma by D. When the pressure inside the, what is the delta P? PT minus PATM. When this PT will be higher and higher, for example, if PT will be higher and higher, what will be there? If PT will be higher and higher, from here diameter, what we can write? 4 sigma by PT minus PATM. If PT will be higher and higher, this quantity will be what? Higher and higher. What about the diameter of the size of the droplet? It will be smaller. So can I say this statement number 2 is also correct? What about the third statement? Third statement, they have mentioned the pressure inside the droplet or a soap bubble will be less than the surrounding atmosphere. No, it is not correct. It is not correct. It will collapse if it is like that. Then what we can, which statements are correct? Which of the following statements are correct? B, 1 and 2. Everybody getting my point? Tell me guys. Is that clear? Please confirm it. What the answer you guys are getting? Hello, hello, I'm audible. All of you can hear me? Hello, hello. Can I move to the next question? Is that clear? Okay. Now here we will have the question number, for example, we have a 48 question. That is nothing but question number 5, question number 4 for this particular session. Now what they have mentioned guys, just look at into the diagram. Because diagram is not given, so we need to make the diagram. The diagram is not been given. The right limb of a simple U2 manometer containing the mercury is open to what? Atmosphere. While the left limb is connected to a pipe in which the fluid of specific gravity 0.9 is flowing. The center of a pipe is basically, they have mentioned 12 centimeter below the level of a mercury in the right limb. What is the pressure of a fluid in the pipe if the difference of mercury level in the two limbs are 20 centimeter? Now, read this particular statement very carefully because we need to make the diagram here. First of all, what the hint we are getting? It is open to atmosphere, which is mercury. Second hint we are getting, the center of the pipe is 12 centimeter below the level of the mercury in the right limb, and the right limb is open to the atmosphere. So if I make this diagram, so that need to be very clear diagram, right? Because what they are asking, what is the pressure of the fluid in the pipe if the difference of mercury levels in the two limbs is 20 centimeter. If I make this diagram so that you can understand the statement very clearly. First of all, there is a YouTube manometer is there, for example. Now it is clear, it will be clear very soon why I am making the right limb of this manometer tube at somewhat higher height. This is connected to what? This is connected to this diameter of the manometer should be very small. Otherwise, a capillary action will be taking place. Here, this is a pipe. There you have a pipe, and in this one, I am marking there is a mercury. Now, by default, they have clearly given the center of the pipe is 12 centimeter. Sorry, it's 12 centimeter below. This is the center line of the pipe, and it is 12 centimeter below this mercury level. So definitely this height is what? 12 centimeter. This height is 12 centimeter. Just a minute. Here, this height will be 12 centimeter. What else they have given? The difference between the mercury in the two limbs they have given is what? That means this is a total mercury. The red marking which I am doing here. This is the mercury. And the difference of mercury from these two limbs, they have given it as 20 centimeter. both the limbs, the difference of mercury is what? 12, 20 centimeter. And in the basically what we call in the pipe, we have the liquid which is having a specific gravity. If the specific gravity is zero point 0.9, that means what? It's a 900 kilogram per meter cube. The density will be. That is what the liquid we have. That is what the liquid we have. So by define, what we do, we need to find what is the pressure in the fluid. That means here we need to find the pressure at a point number one. So it is very easy now to calculate the pressure. Now what we can do, we can equate the pressure at this as well as this, or we can just do the balancing of this one. What we call the pressure in the left limb at the point A, that is equal to pressure in the right limb at the point B, because both are on the same level. So pressure at point A must be equal to pressure at the point B. What is the pressure at a point A? What is the pressure at a point A? Pressure in the pipe plus what is the rho of a fluid? G into height of the fluid. What is the height of the fluid? It's a 20 centimeter, 0.2 meter. What is the pressure at a point B? Because of the total mercury. What is the total mercury? What is the mercury density? Whether they have given? No, they have not given. So we can take standard mercury density as 13,600 kilogram per meter cube. Rho G into H. What is the total height? 12 plus 20, it's nothing but 32 centimeter divided by 100, because we are converting in meter. So what is the next particular task? The next task is to calculate the pressure in the pipe, which is nothing but 13,600 into 9.81 into 0.32 minus 900 into 9.81 into 0.2. If you try to calculate this value, what is the value you are going to get? 13,600 into 9.81. You are going to get something like a 40927.32. So this is the value you are going to get in Newton per meter square. Just note down. Sorry, this for total value is 20 centimeters. Sorry. If you read the problem, they have given the difference of the difference of mercury level in the two limbs. That means this particular limb as well as this limb, the total difference is what? 20 centimeter. So obviously this total height must be 20 centimeter. This total height from here to here should be 20 centimeter. This value should be 20 centimeter. Obviously this value will be 20 minus 2, that is 20 minus 12, that is nothing but 8 centimeter. So definitely we need to modify these values. Here it should be what should be the value here? It should be 0.2, it should be 0.8, right guys? And this value need to be changed here. This value need to be changed. Now what is the value you are going to get? 13,600 into 9.81 into 0.2 minus 900 into 9.81 into 0.8. So you are going to get 19 8 centimeter, right? 8 centimeter is 0.08 meter. So 13,600 into 9.81 into 0.2 minus 900 into 9.81 into 0.08. So you are going to get something like a 25 976.88 Newton per meter square. Now, if you try to convert in, what they are asking, Newton per centimeter square. So, if you try to convert in centimeter, what you can get? 25976.88. 1 meter will be 100 centimeters square. So, you have to divide with the what? Tell me, guys. 1 meter will be 100 centimeters square. So, it's nothing but 10 to the power 4 centimeters square. So, 25976.88 divided by 10 to the power 4. So, you are going to get 2.597. What is the pressure in the pipe? 2.5976. That should be the value in Newton per centimeter square. So by looking at the option, which option is correct? C will be correct. C will be correct for this question number 48. Right? Now, not only question number 49. Question number 5 for according to this particular session. So here, what we can do, we can read the problem. The barometric pressure at the sea level is 760 mm of Hg, while that on the mountain top is nothing but suppose we have the mountain. The pressure at this particular point is nothing but in terms of mercury, it's a 735 mm, 735 mm of mercury, and pressure at the sea level here it is given as 760 mm of Hg, for example. They are asking what is the height of this mountain. What is the height of this particular mountain? Assume the air density as 1.2 kilogram per meter cube. So again, what we can do, we can take this as a point B, we can take this as a point A, and we can take the difference of this pressure, and then we can calculate the values. Then we can calculate this particular values. Everybody know from the hydrostatic law. From the hydrostatic law, everybody know that the pressure at a point A must be equal to pressure at a point B plus rho GH. Rho GH. But here they have not given the pressure at a point A and point B in terms of kilopascal or Pascal. They have given in terms of mercury. So what we can do, it's a very good thing for us. Directly we can calculate in terms of uh, mercury height, whatever the height is being given. What is the height which is being given? So we can convert. There's no problem. We can convert this one in terms of pressure. What is the pressure at a point A? Rho of mercury, G into height of the mercury, 760. So that let's keep it like that only. What is the pressure at a point B? It's a rho of mercury, G into 735. Now density of the mercury, it's a standard value is nothing but 13,600 kilogram per meter cube until unless it is given in the problem. So what we can just write PA, that is nothing but 13,600. What is the pressure at a point B? Pressure at a point B will be 13,600 into G into 735 plus rho of air G into height. So what we can do here is that we can cancel G value from this sides and we can just do the balancing here. 760 mm, but if you try to convert in meter, I need to divide by 1000. So 13,000 760 minus 735 into 13,600 divided by 1000. So I'm going to get 340. 1.2 times of H. So from here, what is the H value? It's a 283.33 meter. What should be the answer? The answer must be B. Please note down. Now the answer for this particular question must be B. It's a simple hydrostatic law based problem. You can also think when we start moving in the vertical upward direction, the pressure will be start decreasing, and that is what happening. At the bottom surface, at the sea level, we have 760 mm of Hg, but at the top, it is having 735, which is less than 760, right? Because according to hydrostatic law, we know that dP by dH must be directly proportional to rho g. Accordingly, if you have the constant density fluid in isothermal medium, the pressure is directly proportional to H. That means if H is increasing, the pressure will increase. That is a statement regarding the hydrostatic law. Hold on. So moving to the next question, that is the question number 50. That is nothing but question number 7, question number 6, probably the question number 6 here. The square aperture here in the vertical side of the tank has one diagonal vertical, and it is completely covered by the plane plate which is hinged along one of the upper side of the aperture. The diagonal of the apertures are 2 meter long, and the tank is containing the liquid which is having a specific gravity 1.15. The center of aperture is 1.5 meter below the free surface. What is the position of a center of aperture? H bar Cp they are asking. So let me draw the diagram first of all. The square aperture in the vertical side of the tank. That means if I draw the side of the tank, for example, this is the free surface level of the liquid, and we have the aperture which is having a shape something diagonal like this, which is having a shape. This is the vertical diagonal, and there is a horizontal diagonal. These two values they have given us 2 meter, and the height is also given as 2 meter. And the centroid of this G is value from from the free surface of the liquid is 1.5 meter below of it. That is the data they have given. They are first of all they are not asked the hydrostatic force. They have not been asked what is the hydrostatic force, but they are asking what is the center of a pressure. This value of position of a center of a pressure, H bar Cp, they are asking. So what is the formula for H bar Cp? Already we have discussed in the fluid mechanics. H bar plus Igx sin square theta divided by area into H bar. Remember, H bar is nothing but the distance of a centroid of a plane surface from a free surface level of the liquid. Sin square theta is nothing but the angle made by the plane from the horizontal level, but this angle is what, 90 degree, because this plane is making what, an angle 90 degree. So theta is 90 degree. Area which is being subjected to what, water pressure force. The whole area will be subjected to what, water pressure force, right? Now, can we just quickly calculate what is the area now? Area of this particular square diagonal plates. It's a very easy. There was a square which is something like this, and this was a two diagonal, but the diagonal has been tilted in the vertical and horizontal directions, and this is nothing but 2 meter. If this is 2, this should be what, root 2, then only it is what, 2. What is the area of this square? Root 2 into root 2, which is nothing but 2 meter square. Now the big headache is to calculate what is the value of Igx. Igx is nothing but the moment of inertia of a plane surface about the horizontal centroidal axis, about the axis which is passing through the centroid. Now, which axis is passing? This axis is passing, for example. We need to calculate the moment of inertia of this two triangle about this Ixx. Again, it is one of the very easy, straightforward question. What is the value of Igx? Let me call this as a 1, this as 2. So we can write I1 plus I2. What is the I1, my dear friend? BDQ by 12. What is the B? It's a 2. What is the depth? What is the depth? Can I say it's a 1 meter? If the total height is 2 meters, then what about the height from here to here? Let me just call A, B, C, D. Then what is the height of A to G? That means I'm asking this particular height from here to here. This was this height. See, you know that this value is what? This is the total value root 2. This will be 1 upon root 2. This will be 1 upon root 2. Then what about this one, guys? 1 upon root 2 whole square plus 1 upon root 2 whole square under root of that, that is the height of AG, height of the AG. So 1 upon 2 plus 1 upon 2 under root of that is what? Height of AG. Then AG is what, guys? It's a 1. It is a 1. So 2 into 1 cube divided by 12 plus 2 into 1 cube divided by 12. So what we are going to get, guys? 1 upon 6 plus 1 upon 6, which is nothing but 1 upon 3 meter to the power 4. So this is nothing but total IGX. This is the I1. This is the I1. Because we have the two triangles, right? Now what is the H bar CP? H bar. What is the H bar value, guys? H bar is given as a 1.5 meter directly in the problem. See that? The center of aperture is 1.5 meter below the free surface. So directly they have given. H bar is 1.5. So what is the value now? 1 upon 3 by 2 by 1.5. So if you try to calculate, you are going to get 1.611 meter. That should be the answer. Meanwhile, we got the answer as 1.611 meter. That is the correct. But what about if I'm asking you, this is a problem number A. What about the problem number B? What is the hydrostatic force? If I'm asking second question, what is the hydrostatic force? That is nothing but rho g into h bar into area. Now, what is the rho? Already they have given the specific gravity 1.15. Now, what is the meaning of specific gravity? Rho of any fluid to the rho of standard fluid. What is the rho of standard fluid in case of liquid? It's a water. Then what is the rho of fluid? 1.15 into 1000. So if you try to multiply with the 1000, you are going to get 1150 kilogram per meter cube. So 1150 into 9.81, 1.5 into area is what? 2. So if you try to calculate 1150 into 9.81 into 1.5 into 2, so you are going to get hydrostatic force as 3.844 kilonewton. That should be the answer. Again, they have not asked, but I'm just saying you, if in case they would have been asked, this would be the answer. So the answer for this question is what? B, 1.611 meter. What is the position of a hydrostatic pressure force exactly where it is acting on a vertical plate, vertical side of the tank, from here to here? Now we will try to solve the next question now. Not on the next particular problem. Again, this particular problem they are asking based on the stream functions. The stream function for a two-dimensional flow is nothing but 2xy. What is the velocity at a point P? What is the velocity at a point P? We know that a stream function will only define for 2D flow, not for 3D flow. And we also know U is equal to what? Minus dou psi by dou y. And V is what? Dou psi by dou x. That is the velocity component based on the V. Now, what is the value of U? Minus dou by dou y of 2xy, which is nothing but minus 2x. And what is the value of V? Dou by dou x of 2xy. So V value will be 2y. Once we got U and V at a point 2, at a point 2 comma 3, what is the velocity? X component of velocity? Minus 4. What is the V? This is a 4 unit. What is the V at 2 comma 3? It is 6 unit. Now what they are asking total net velocity. You know that the net velocity is what? The total velocity vector is what? U I cap plus V j cap. And if you try to find the magnitude, it is U square plus V square. So minus 4 square plus 6 square. If you try to calculate, it's 16 plus 36 under root of that, you are going to get 7.21. unit per second, unit per second. This should be unit per second. B must be correct. Again, if the calculator is not being allowed, then you should know how to calculate, under root of 52. You should be knowing this particular thing, right? You should be knowing the procedures like 7, 7, 49. Again, we have 3, and then if you write dot here, then 142. Then what we can get, guys? 4 here, 284. So 7.21, something like that you will get. You should be knowing how to calculate the under root of 52. If you're not knowing, it's a very simple. 52, see, we are getting it's under root of 52, right? 52 is very near to what? 49. Under root of 49 is what? 7. So definitely it should be slightly more than 7. 7.21, not 7.61, right? So that should be the answer for question number 51. Note down. Now here we have another good problem based on the forced vortex. Forced vortex. See, this particular problem already being asked in GATE examinations, but they have repeated, they have taken directly the question from the GATE. Here, what they have given? They have taken one circular tank, a closed circular tank. This circular tank is getting rotated about certain axis, omega radian per second, and is given. Very quickly, we can calculate omega, 2 pi n by 60. So omega will be 2 pi into 200 divided by 60. So omega from here we can calculate like 2 into pi into 200 divided by 60. So we are going to get 20.944 radian per second approximately. Once we got the omega, what is the next thing that we need to take into the account? That is the diameter. What is the diameter they have given? Diameter is given as 0.2 meter. The height of this tank, which is containing the liquid here, it is filled with the liquid. Complete liquid is there here. The height is given as 0.15 meter because 150 mm, so it is 1.15 meter. What is the total pressure force exerted by the water on the top of the cylinder? Let me consider top of the cylinder, for example, at a point A here. See, you should be knowing what is the force vortex equations. You should be knowing what is the general equation what is the fundamental equation of a vortex flow. For a vortex flow, what is the fundamental or general equations, right? So here, fundamental equation for forced vortex flow. So dP is equal to rho v square upon r into dr minus rho into gz. This is the complete equation we have, my dear friend. This is the complete equation we have. No doubt. But they are not asking, basically, there's no variation of a height. Because whenever the tank is rotated about certain axis, there will be basically we are calculating from the center to here at a point A, from 0 to here. So we are taking both the point on the same level. So this will not be coming into the picture. So what is the dP here? Rho v square upon r into dr. Can we write in terms of, for a forced vortex motion, we know that v is equal to r omega. Everybody know that. So what is the dP? Rho r omega square into dr. Rho r omega square into dr. If we try to integrate for finding the pressure force, what we can do? We can just write like this. For a pressure force, we need to integrate dP into, see, because now if you try to see if you take a small elemental area, if we try to take a small elemental area, now what is the small elemental area? What is the small elemental area? So 2 pi r into dr, dp into 2 pi r into dr. Now if I integrate from here to here, like 0 to r, I'm going to get total pressure force. So what we can get, guys, rho into r omega square into 2 pi r dr, which is nothing but 2 pi rho omega square r square into dr. Or here, what we can say, instead of doing like this, we can also, because here, whatever the pressure value is there, that pressure quantity here, little bit of modification is required. See, understand. Here, what is the value of, first of all, P? What is the value of P at a point A, for example? At any radius, for example, R, from the center of rotation, what is the pressure? First of all, that we need to get. We need to integrate it. If I integrate, I will be getting what? From 0 to R. I will be getting my difference 0 to P. So I will be getting P as rho into omega square integration of R dr, which I am going to get what? I am going to get rho into omega square 0 to R. I am going to get rho R square point A. Now might be different. What we can do, we can just integrate to get the value of pressure force. What is the pressure force? The pressure force we can get dFP, which is equal to what? P into area, elemental area, 2 pi r into dr. And that we are doing integration from 0 to capital R. We cannot easily find directly the pressure force exactly without doing any integration, because now it's a radial distance, and now this radial distance from the centroid, it is varying from center of the rotation to extreme end. It is keep on rotating, right? It's keep on changing. So directly we cannot do that. We cannot write the pressure force as P multiply with the area, because see, when we are able to write like that, when the pressure is acting on a fixed particular area, and that area is at the radius what? R, from a center of rotation. The whole area is there at a fixed radial distance, then we are not required any integration. But the area is what keep on changing with respect to radial distance, because it's a function of a radius. So definitely we need to perform the integration. So what is the pressure force here? Rho omega square r square by 2, 2 pi r dr. Again, r we can take inside. So directly, if I write the formula, rho into 2 pi rho omega square r to the power 4 by 4 divided by 2. So what we can get? Pi rho omega square r to the power 4 by 4. That should be the value of a pressure force exactly on the top surface. So if you put the value, what is the value they have given? Pi. Now what is the value of rho in the problem? It is a water. So water density is what? 1000. Omega, everybody already we have calculated 20.944. What is the radius? Radius they have given 0.1 meter divided by 4. So if we try to calculate what is the pressure force, pi into 1000, this is a square, 20.944 square into 0.1 to the power 4 divided by 4. So we are going to get 34.452 Newton. That should be the value of a pressure force. Remember, if they would have been asking what is the pressure force exactly on the bottom surface at a point B, then we would have done like this. Already we know pi into, suppose at the bottom at a point B, pi rho omega square r to the power 4 by 4 plus, because of this total height, there must be some static force must also be acting, right? Which is nothing but what we can write? Rho gh, and what is the constant area, right? What is the projected area? Pi r square. But this quantity will not be coming when we are calculating at the top surface, because height is 0. There's no liquid height is there. So only this term will be coming. So accordingly, which option is correct? A must be correct. So here we are telling with respect to no, basically by taking the derivation also, so that you can understand. from where exactly it is coming. 34.44 Newton, that need to be, correct answer. All these questions are already given in the SK SOM and some of the standard textbooks, right? Now, what is the next question, guys? A torpedo is found to move, basically, no, basically, if I draw the rough diagram, here, if I just make the rough diagram of it, the torpedo, I'm just making the very rough diagram. Let's say it is moving in a sea level at a depth of, for example, 15 meter, and it is a sea level. So sea level basically having slightly more density than water, normal water, which is given as 1025 kilogram per meter cube. By default, what they are asking, what is the value of pressure at the nose? What is the value of pressure at the nose? So you know that it's a very easy to calculate it. Whenever it is moving at a speed of 25 meter per second, the torpedo is about to move, is found to move in a sea at a speed of 25 meter per second when it is submerged at a depth of 15 meter. What is the pressure at the nose? You remember one concept, whenever any object is there, for example, any object is there, whenever this object is moving like this, whenever the fluid is attacking or basically striking the nose of any body or contact point, when it is contacting, at that particular point, the net velocity is zero. Then at that particular point, whatever the pressure is there at a point B, for example, the total pressure will be stagnation pressure. Stagnation pressure, everybody know that. We know that it's a static pressure plus dynamic pressure. What is the static pressure? Rho gh. What is the dynamic pressure? Half of rho v square. Because dynamic pressure, we know that from the pitot tube concept, right? So from here, what is the total pressure at a point B or at a nose? Because whenever it is going to move, it is going to strike the fluid, stationary fluid, for example. So at that particular point, it is going to have the zero velocity. And whenever the fluid is brought to at the rest conditions at a particular surface contact point, then whatever the total pressure is there, that is nothing but stagnation pressure, right? So rho is what? 1025 into 9.81 into height is 15. They are asking in kilos, so I'm dividing with what? 1000. Half of rho is what? 1025. Again divided with the 1000 so that we can get in kilopascal. Velocity is what? 25 square. So if you try to do this one, 1025 into 9.81 into 15 divided by 1000 plus what we can get, 1025 into 25 into 25 over 2000. So approximately we are going to get pressure at a point B as 471.14 kilonewton per meter square. So approximately which option is correct? A will be correct. Don't know. Oh, 71.2 kilonewton per meter square. That will be correct option. Now moving on to the next question. Consider a following statement. Consider a following statement regarding the control volume in the application of linear momentum equation. Everybody know that for a linear applying the linear momentum equation, let's say we have the variable diameter pipe like this, and in this pipe the fluid is flowing, for example. First of all, for analysis of the forces, we need to select a control volume. we need to select a control volume. There is no doubt. This control volume is nothing but it is a boundary that are tangential to the direction of a flow at the inlet outlet. Yes. See that? It must be aligned with the flow directions. So first statement must be correct. First statement must be correct. It is inside the flow boundary and has some alignment as flow boundary, right? It has to be aligned with the flow directions. We cannot take any random control volume. But selecting a proper control volume is very essential to get the correct answer regarding linear momentum equation. So second should also be correct. If the magnitude of the boundary forces are not known, their resultant is taken as a reaction force R, which is the force acting on a fluid control volume due to the reaction from boundary. It is also correct. It is also correct. This statement is also correct. Because see, first of all, for finding the forces, you know that when the fluid is flowing, the fluid will exert some kind of forces on a pipe. This fluid will exert some forces on a pipe wall like this. Opposite of that, the pipe will also exert some reaction force according to Newton's third law on a fluid element. And that can be found out very easily by finding the forces on a control volume. So that is also correct statement, right? Whatever the liquid will exert the pressure force, that is the applied force. What would have been the force exerted by the pipe onto the fluid element? That is the reaction force. That reaction force we can just calculate by using the control volume analysis. So that is the correct statement. Read that. If the magnitude of the boundary forces are not known, there is a resultant is taken as a reaction force R, which is the force acting on a fluid control volume due to the reaction from the boundary. Yes, it is correct. So 1, 2, and 3 all must be correct for this particular question, right? So it is one of the straightforward, but while looking at this statement, look somewhat not easy, right? But it is one of the easy question, right? Now coming to the this particular question, consider question number 75. Consider the following statement regarding the static pressure in a flow measurement. For the flow of a real and Stokesian fluid, the static or thermodynamic pressure becomes equal to negative arithmetic average or normal stress at a point. Yes, by the derivation of a Navier-Stokes equation, everybody must be very clear with this statement. There is no doubt. For a real and Stokesian fluid, the static or thermodynamic pressure becomes equal to negative arithmetic average of the normal stresses at a particular point. Right? Thermodynamic pressure that is equal to mechanical pressure. What we write? We write sigma 11 plus sigma 22 plus sigma 33 divided by 3, and that is the negative of that. It's obviously correct. This statement obviously correct. When you can come to know about this statement, when you know proper each and every step of Navier-Stokes derivation. That is very, very essential. Very, very essential. Mechanical pressure and thermodynamic pressure both are equal. Generally, they are equal, except some few cases. Second statement, what they have mentioned, the static pressure at a point in a fluid flow is a pressure which would results in the fluid brought to the rest isentropically. No, it's incorrect. Wherever the fluid is brought to the rest isentropically, at that particular point, the total pressure is what? Stagnation pressure, not the static pressure. It has to be stagnation pressure, right? It is an incorrect statement. Third statement, what they have mentioned, the static pressure is obtained by adding the stagnation pressure and dynamic pressure. No, it is incorrect. Because we know that stagnation pressure is equal to static plus dynamic. So how to get the static pressure? Stagnation minus dynamic. So again, it is also incorrect. So which statement is correct? Only first statement is correct. One only is correct. Remaining statements are incorrect. And the combination of that is also incorrect. Right. So that is regarding fluid mechanics. And according to me, the review regarding fluid mechanics is that it is not that easy and very straightforward. You have to do the numerical also. You should know the theoretical you should have a theoretical understanding of the subject. Then only you can attack this particular subject. If this would have been the level of each and every subset, of this DGCA paper, then cutoff would be low. Thank you all. Any doubt, you can just let us know. And if you're finding this session to be useful, then you can thumbs up.